Okay, so for number 1, as well as number 3, that looks pretty similar to me. It's just a lot of geometry, like, hey, what's the volume of a cube? We know it's s cubed, s times s times s, length times width times height, and all the sides are, of course, the same for a cube. Take the derivative, which is 3s squared. Of course, plug in 1 and 5 into the derivative, you get that. And just give the units for the derivative. Remember, volume is in inches cubed, and of course, dimension is just at inches. That should be pretty straightforward for number 1. For number 3, it's kind of the same thing, and I don't see the answers. Oh, there they are. So that one's kind of a fun one. And actually, we might, it all depends on what we do in the second semester, as well as what the AP tells us, or some of the college board tells us with the AP exam. There is a particular unit right near the end of AP Calculus where it's very geometry heavy, and you have to be pretty comfortable with like rewriting geometry formulas. So I guess we'll go over this one, but if we may have to revisit this in the spring, if we do that unit that I was just talking about that involves a lot of geometry. But remember, area of triangle is easy, 1/2 times base times height. You guys should know this. What may not be so obvious is that for an equilateral triangle, how do you get the base and height to be the same variable? Now, let's say I call each side the triangle S. If I do that and drop the altitude, here I got my height. And of course, that's 60 degrees, right? Remember, equilateral triangle, all the sides are the same. So all the angles are the same. And you have to split 180 equally, so that's why you get 60, 60, 60. That's 60 right there. And if you remember your ratios, if that's S over 2. Obviously, that took half of this, right? And then this is S root 3 over 2. You could do Pythagorean theorem, or if you just know your ratios of 36 and 90 triangles, you're totally set there. So my height is S root 3 over 2, and the base is S. So the area can be expressed like this. Area equals 1/2 times your base, which is S, times your height, which is S root 3 over 2. Altogether, it's going to be S squared root 3 over 4. So that's how you can actually get the area in terms of the side length. Then to take a derivative, that's easy. Just move the 2 to the front. So 2s times root 3 over 4, which reduces to s root 3 over 2. So that's how I can express the area of an equilateral triangle, sorry, the derivative of the area, or the rate of change of the area with respect to side, if I did it in terms of one variable. Then, of course, plug in 2 and 10, you're good. And it's inches squared per inch. So that's how that works. So hopefully that gives you kind of an idea of what we're dealing with in these problems here. There's still problems on linear motion. And I think 5 finally touches on that, as well as 7. So let's look at 5 and 7. Now for 5, geez, I have to go. Let me, I left my textbook in my car. That's okay. It says here to plot S versus T, sketch smooth curve, and then as soon as this curve is smooth, blah, 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 there's other stuff we have to do. Okay, so again, I have to do a curve and estimate the velocity. Got it. Okay, there we go. So yeah, it's kind of open-ended somewhat, because I mean, you are estimating the velocity. So what you could do is just make a coordinate plane, plot some points like 0, 12.5. We'll say that's 12.5 right there. 0.5, 26. One, 36.5. So you want getting a curve that kind of keeps increasing, I guess. I obviously didn't leave myself enough room there. And then you're asked to estimate the velocity. So you're just simply going to just, draw a tangent line, just kind of say, okay, what's the slope of that line? So that's kind of what you're doing. Now you could, if you so desire, and we talked about this with the notes, that you could estimate by maybe taking the slope between these 2 points for velocity at 1. So you could do like s of 1.5 minus s of 0.5 over 1.5 minus 0.5, which would be 44 minus 26 over 1, or 18. So you could do that too to estimate the velocity at 1. And likewise for 2.5, just take the slope between 2 and 3. Or for 3.5, take the slope between 3 and 4. That might be a little bit better than just drawing a curve and just drawing a tangent line and guessing what the slope is. That might be just a better way of estimating. Like we've done examples, I think 6 and 7 of the 3-4 notes. And I did talk about that on Tuesday, how they do as an AP style problem. When I say they, I mean the College Board. For this one here, they're asking you to use graphical technique section 3.1 example 3. I don't know what that means. To graph the derivative. Okay, we know how to graph derivatives. We've done that before. The graph of population is reproduced below. What unit should be used in the horizontal and vertical axes of the derivative graph? Well, remember, a derivative is a rate of change. So if you do a derivative graph, I'll kind of do a quick sketch. I'll call this like P prime. That's going to be the number of flies per day, it's the rate. And of course, you have days down here. And it looks like the slope is always positive, but it's kind of small slope. I think it's pretty steep around like, say, 25 or so. Maybe like a slope of like 1 or 2, and then it kind of shallows out. So it probably will look kind of like that, I would say. And maybe that's like at 1, maybe that's like at 0.5. You know, just kind of estimate how that would look. Then the question is asking us from part B, when does it seem to be increasing the fastest? Definitely over here. Because that's your steepest slope of our tangent line. And probably shallowest, probably over here, or slowest up here. So it kind of levels off after a while. So I'd probably say slowest. Somewhere around there, maybe at 0, you could say. I mean, I just kind of arbitrarily drew a dot at like 7 or 5, but you could probably stick right here or like right here. Question in the chat. Why is the acceleration velocity speeding up when they have the same sign? Number 9. Okay, let's do number 9 now. Someone's asked about number 9. So now we're kind of warmed up. All right, so let me move on to the next image. Okay, number 9. And again, I'm kind of taking my time at the homework review because you know, we have the time to do that because I'm not going to do all 4-1 today. So, and I didn't quite go over homework with you guys last time. Okay, let's talk about number 9 here. This is a good one. After that, then I might just see if there are any specific questions after number 9. But number 9 is kind of the quintessential problem for section 3.4. So the accompanying figure shows the velocity of a particle on a coordinate line. Okay, when does a particle move forward, moves backward? Okay, so this is obviously a velocity graph, right? So just remember what kind of graph you have. We have a velocity graph. So when velocity is positive, we're moving forward. So what's the connection to that to the coordinate geometry? That means when the y coordinate is positive. So I'll get a highlighter. I'll highlight in green as moving forward. So green is forward. This is the beauty about zooms, that I can actually color code like this. And then red will be negative, and blue will be neutral. So we're clearly moving backwards when our velocity is negative. Now, before I do the speeding up and slowing down, let's talk about the interval for moving forward and moving backwards. That should be really easy now. I'm moving forward, obviously from 0 to 1. Now I'm going to actually do a bracket at 0 and a parenthesis at 1. I'm doing a bracket at 0 because our velocity is positive at 0, right? So we are moving forward initially. But at 1, we're at rest. So we're not moving at all at 1. So here, we're at rest. We're actually at rest after 7 seconds, from 7 to 9 seconds. We're not moving at all. We have a 0 velocity. Question in the chat? Yes, I'll go to number 11, no problem. Now, moving backwards, sorry, not to move forwards. Also, we do a union, and from 5 to 7, and you have to do parentheses around 5 and 7 because, again, you're momentarily stopped at 5 and 7. You're not moving forward nor backwards. So you have that. Now, backwards is from 1 to 5. And again, I'm doing parentheses there because you're not moving at all at 1 to 5 exactly. Now, the speeding up and slowing down. The speeding up would be if you are having a positive velocity and your acceleration is positive, or velocity is negative and acceleration is negative. So this morning I came from Redwood City, and I didn't take El Camino, I took one of the side roads, but let's say I took El Camino, right? And let's say I consider El Camino to be the positive, sorry, going south in El Camino towards Sacred Heart Prep from Redwood City. So I'm passing the Target, I'm passing the, I don't know, all the nice homes, whatever, right? So if I'm going south in El Camino, I consider it to be a positive direction. Now, let's say I have a kind of an open road in front of me, and I step on the gas, and now I'm going from 30 miles per hour to 40 miles per hour. Clearly, I'm accelerating, right? My acceleration is positive as I put my foot harder on the pedal, and I'm going faster, right? So obviously, my velocity is positive. I'm consider the positive direction to be going towards Sacred Heart. So it depends how you consider. So you have to think of your frame of reference. Like going towards Sacred Heart from Redwood City is positive for me, and I'm stepping on the accelerator, so I'm going faster. So my speed went from 30 to 40 miles per hour, let's say. So I'm speeding up when this is happening. Now, let's say I realize I forgot something at my house. So I make a U-turn. Now I'm going the other direction. So now that's a negative direction, but I'm trying to get back to my house really, really fast, and really quickly, right? So my acceleration will also be going in the negative direction because, again, I'm increasing my velocity in the opposite direction. So essentially, we have to look for positive y coordinates, because that's positive for positive velocity. For positive acceleration, I'm looking for a positive slope of tangent line. So where is that happening? Definitely it's happening from 5 to 6. From 5 to 6, my velocity is positive, obviously because I'm above the x-axis, and my slope is positive. I have a positive slope there. Now, I'm also speeding up, excuse me, from 1 to 2. Here, my velocity is negative, and my acceleration is negative, so I have a negative slope there. I'm slowing down here. Now, I'm going to get to that in just a little bit. But I'm speeding up only from 1 to 2, because the velocity and acceleration are the same sign there. Velocity is negative, acceleration is negative. That's like going the opposite direction, going faster in the opposite direction, because when your acceleration is negative, your velocity is negative. What that means that your acceleration is helping you go faster in that direction. And of course, my velocity is positive, my acceleration is positive from 5 to 6. Now, for opposite directions, when you're slowing down, that's when your velocity is positive, your acceleration is negative, or vice versa. So what's happening is that your acceleration is working against you. So like if I hit the brakes, I'm moving forward still, but I'm slowing down. Or if I turn around, but my acceleration is still pointing the other direction, you can kind of think of like the wind, right? Think of that if that helps. Like let's say, for example, you're trying to think of like a sport where, well, I mean, there's a lot of sports where wind can impact your results. But just say, for example, or say you're playing golf. Let's say that's it's a good sport. But if you're hitting the ball, if the wind's going against you, your ball's not going to go as far, right? So you can kind of think of the wind's probably slowing down the ball's movement. Whereas if I'm going with the wind, the ball's going to carry the ball further, and so there's some sort of acceleration. So kind of think of that way. Or like if you're on a river and you're going against the current or with the current, maybe that might help. So think of the current or the wind like the acceleration. And then, of course, where direction you're heading is your velocity. So when we're slowing down, excuse me, that's going to be from 3 to 5. and also from 6 to 7. And it totally makes sense because from 6 to 7, you're going from velocity of here down to 0. And likewise, you're going from a speed. Remember, speed is the absolute value of velocity, so you actually have a high speed here. Even though it's negative, that's a high speed. Because remember, speed is the absolute value of velocity, and you're going down to 0. So hopefully that helps a little bit with part A. And I'm surprised that A was asked before B, because you really should have done B before speeding up and slowing down. The expression is positive from 3 to 6. And you're not going to include 3 and 6 because acceleration is derivative of velocity. You have corners at 3 and 6. You don't include the corners. And also, we're having a negative acceleration from 0 to 2, and also from 6 to 7. And we have no acceleration from 7 to 9 because we're not even moving at all. There's no change in the velocity whatsoever. Now, if you had a flat velocity, like say it just stayed consistent, like at 1 meter per second, you'd also have a zero acceleration there too. The greatest speed, kind of hard to tell. I'd say either here or here, because they didn't give us tick marks for the vertical axis, so that's kind of hard to tell. So I'd say the greatest speed would be either here or there. And then when does it stand still for an instant? Obviously at 1.5. 7 included, or it's just 7 to 9 included. Okay, any questions about number 9? Nope, okay. And I think what I might do for homework over the weekend, I might give you just a few problems from chapters, from sections 3, 4, and 3, 5, maybe for the chapter review, just to kind of give you guys a little more practice on that, because we are going to get into some pretty unique stuff to, later today on section 4.1. All right, so someone did ask about 11, so let me go over that too. And then after that mail, then I'll just take requests for other problems from 3, 4. Okay, the graph for 11 is right there, which kind of stinks because can't really, I'll have to go back and forth. So let me zoom in, give me 1 sec. So you got your velocity from 0 to 10, okay, blah, blah, blah. And what are the questions asking? Okay, actually, let me drop this down really quickly on a piece of paper for myself. Then I'll replicate on the screen. That's 8, 10, crosses at 2, 4, 6, probably x-intercept 7, 3 meters per second, seconds. Okay, I think I've got it. Cool. Excuse me. All right. So I'll try to replicate the graph on my screen here. Now let me zoom in. Okay. So it looks like there are 4 parts to this problem. So when does the body reverse direction? Now the graph looked like this. So I'm going to replicate the graph up here. So this is 3. This is -3. I'll do 5 tick marks, 2, 4, 6, 8, 10. And a little premature. Okay, kind of crappy graph, but so be it. You reverse direction at 2 and 7, obviously, because that's when the velocity is 0. Remember, you're momentarily, if you're going to change direction, you have to stop the car. Right? You can't just all of a sudden, and even if you're like a stunt car driver, you want to do something fun like that in an open parking lot, you still have to, you're still momentarily stopped, right? Like, I mean, you hit the brakes hard, you can turn the car around, right? Otherwise, your car's going to flip over, and then you'll really be stopped after you crash several times. When the body's moving at a constant speed, definitely from 2 to 7, it seems, or sorry, from 3 to 6. You just have to look at the graph carefully. It seems that here's 3 and here's 6. So it's just a constant velocity there. The speed, graph the body's speed. So that's just the absolute value of velocity, right? So you're just going to do this. And then at 3, kind of, 2, it bends up like this. And at 7, it bends up again. Or it just does that. So basically, you take this portion and flip it over the x-axis. That's what you do for part C. And then graph the acceleration. The acceleration is not going to be continuous because we have corners. So we're not differentiable at the corners. So graph the acceleration, that's a great question. I love that question. Let's use black instead. It's a little easier to see. So it seems that this slope is going to be 3. And this slope, kind of hard to tell, maybe -3. That's probably 0. That's probably a slope of probably 3 again. And then probably -3 again. So I'll probably do this. And you're going to do open circles here because we're not differentiable at corners. Now, for the left endpoint, you can assume you're differentiable using the appropriate one-side derivative. So I'll leave that filled in. And then -3 from here to here, then 0 from here to here, then +3 from there to there, and then -3 from there to there. So we'll say this happens at 1, let's say, and then 3, and then 6, then 8, and then 10. Actually, that's probably -3/2. So I'll probably make that a little higher for that last segment. So again, it is an estimate, of course, based upon the graph, and I'm just replicating the graph from my memory, so of how it was on the previous page or on the lower left corner of that page. So, but that's how you would do it because those are actually slopes of the velocity graph. So that's 11. Okay, so looking at the time, I can't keep going over all the problems here, but I have gone over a good chunk. So I'll kind of just take requests for anything else from 3-4 before I talk about 3-5. So are there any requests among 13, 15, as well as 19, 21, 23? More than happy to kind of quickly talk about any questions you may have had about those problems. 15 looks like it's like example 4. Someone's going up then down. 19, more in particle motion. We'll look at that one kind of quickly. Find its place in the first 5 seconds. That's just a change of velocity, just so you know. So that's just S5 minus S0. So S5 would be 25 minus 15 plus 2, which is 12. That's S5. S0, of course, is 2 if you plug in 0 for t. And you got to take the difference. So that's displacement. It's a change in position. Average velocity is S5 minus S0, but then divide by 5. Instantaneous velocity is your derivative. So that's S prime of 4. So we got to plug 4 into that because they said so. Acceleration is going to be S double prime of 4. So you got to do the second derivative now, or derivative velocity. Changes direction. Obviously, this is when S prime is 0. S prime is easy. That's just S prime of t is just 2t minus 3. So of course t equals 1.5 when the derivative is 0. And your second derivative is just straight up just 2. So it looks like we're always accelerating here. So that's that one. And where is the particle when S is at a minimum? So you'd have to find the vertex for this, which is not so bad because you can actually factor it. And your x-intercepts are 1 and 2 for the position graph. So then your y-coordinate, your x-coordinate of the vertex is 1.5, which kind of makes sense because that's where our velocity was 0. And then you plug 1.5 into the function itself, the position function, to get the lowest position. So that's a great problem too. I like 19 a lot. Might be something I would probably add. To our exam, what we have later. And then of course, 21 and 23 are kind of the same thing. Okay, any burning question before I move on to 3.5? No? Okay, just really quick, 3.5 should be pretty easy. Those types of problems. And I kind of like how I did this one. I might try to do the future homework this way because I think it'll be easier for me to kind of navigate during class. And you might just like the fact that this is a really light, a small file, and kind of easy to see everything on one page. 26, yes, let's talk about 26 here. Now 1 through 6 are straight up just doing derivatives. Some involve product rule or a quotient rule for 7 and 10. Hopefully you guys are comfortable with that. 21, we had a problem kind of like that in the notes. Just finding the slope of a tangent line, normal line, and of course writing the equation of those lines. Let's do 10 first. Someone's asked about 10. Okay. So really quickly, you're doing quotient rule. So remember, it's a low d high. So your low is 1 plus sine x. And I'll do the derivative in red so it stands out. So the derivative of cos x is negative sine x. And there is a times there, just so you know. But it's a negative sign. Maybe I'll put that in parentheses if that helps. And then minus, because that's part of quotient rule, high d low, so the cos x. And I didn't really leave myself enough space here, so I'll have to kind of tuck it in. You're being multiplied by the derivative of 1 plus sine x, which will be 0 plus cos x. Derivative 1 is 0, derivative sine x is cos x. You'll have to squeeze that in down here. And of course, divide by the bottom square. Now, at this point, you are technically done. But yes, I would like to simplify, because what I'll probably do is this is a multiple choice question, forcing to simplify. Now, yes, you could use a calculator to verify your work. You could do the end derivative for a particular x value, or maybe graph the end derivative, and then graph each of the choices multiple choice questions, see which graph would match with the end derivative graph. You could do that, I suppose, but I always like to see your work too. So you want to make sure you're comfortable doing this by hand. So distribute the negative sign there, and do negative cos times cos, that's negative cosine squared x. Okay, so if you had a hard time with simplifying, it's probably because it was an identity issue. You see negative sine squared and negative cosine squared. First of all, I could probably just factor a negative from the whole thing and just write that. The reason why I can get away with that is that the negative off to the left is like saying -1 times that whole thing. And that -1 only goes to either the top or bottom, not to both. If it goes to both, then it's positive, right? So that's where that negative comes from over here. It's like you pull out the negative from all three of these trig expressions. And you should know what this is. That's 1, right? Sine squared plus cosine squared is 1. We should know this. So that's to get 1 plus sine x up top. Now at the bottom, you have 1 plus sine x squared. So you got 2 of these 1 plus sine x's, right? 1 plus sine x and another 1 plus sine x. And that cancels. And that's you're left out the 1 up top, so it's -1 over 1 plus sine x. So that's using the quotient rule. For 26, yeah, the proof. So I didn't do this in the lecture notes. So if I go back to the lecture notes, there was a process we did for proving the derivative of tangent. So you might remember that. Lecture notes, filled out notes, 3, 5. Again, you might remember that we did this, right? And I do have the video in Schoology as I went through step by step. sorry, in YouTube that I shared a link in Schoology. But yeah, you know, I just kind of like did like a little quotient rule thing and worked it out. So that's exactly what we're going to do here. Let me do for maybe one of these, and maybe that will help you understand how to do part B. So let me do part A. So actually, let me do part B instead, because part A is very close to the example. For part A, what you need to do is you need to start by doing this. d dx of cosine x over sine x. Not sine or cosine. Sine or cosine is tangent. And then you just kind of follow the same process that we have in the 3.5 notes. But of course, the numerator and denominator are swapped here. Now here, you can do d dx of 1 over sine x. So we'll do a quotient rule, meaning take derivative of the top, which is 0, times sine x, minus the top times derivative of the bottom, which is negative cos x, over the bottom squared. So -1 times -1, negative cosine is positive, so you have positive cosine x over sine squared x. Now, you can get a little creative here. That's cosine x over sine x times 1 over sine. So I decompose the fraction. Because I decompose the fraction, I know sine, and there's a negative, sorry, forgot about that. Is that in the chat? I forgot the negative. Okay, let me go back to number 10 again. Someone's asked about 10. I'll come back to that in just a sec. So again, 0 times sine x is 0. Then I have -1 times negative cos x. So that's, oh, wait, hold on. Did I do something wrong here? Oh, 0 sine is positive cosine. What am I talking about? Oh, goodness, sorry. Sorry about that. Yeah, so when I'm doing my quotient rule, I do low d high. So low sine x times hot derivative high of 0 minus high d low minus 1 times derivative of sine is cosine. So my bad, that cosine should have been positive, not, well, this cosine is positive, but then there's a negative there, so it becomes negative afterwards. Sorry about that. But again, I decompose a fraction, so I get negative cos x over sine x times 1 over sine x. Well, 1 over sine x is cosecant, cosine over sine is cotan. That's how you can prove that. Now coming back to 10 again. Remember, I did the derivative of the top, which is negative sine x, times 1 plus sine x, minus the top, cos x, times the derivative of the bottom, which is just going to be sine x. Sorry, it's going to be cos x. So what happens is that you have a bunch of negatives up top, and you have that chunk down below. You have a bunch of negatives up top, negative sine x, negative sine squared x, and negative cosine squared x. And you can factor out the negative to have this. And that becomes 1. So it has to get 1 plus sine x. And you have the negative still attached. That negative explains that negative right there. And then, of course, everything else should be fine. Hopefully that answered your question about how come the solution number 2 wasn't negative. No, it is negative. Yeah, it is. Yeah, it's negative. It's hard to see. So, okay. All right, so that covers all the homework stuff. So we did spend quite a bit of time talking about homework, but that's okay. Actually, I was planning on dedicating half of class anyway to that. So I think we're okay there. Okay, so far we're doing okay. We're good? All right. So let me stop this recording.